Control systems often conceal significant energy waste in buildings, allowing major inefficiencies to continue unnoticed for years. This video examines one common but costly example involving variable air volume, VAV, boxes equipped with reheat coils. In a typical VAV reheat system, the room thermostat controls the heating valve for the heating and the VAV box for the cooling. When the cooling is required, the thermostat increases airflow through the VAV box, and the heating valve is closed at that time, so there's no conflict of cooling and heating. When heating is required, it is modulated with the reheat valve, and the VAV box also maintains the minimum airflow setting to satisfy ventilation and indoor air quality requirements. Problems arise when the reheat valve seat becomes defective. Even though the valve is commanded closed, wear and tear on the valve seat or disc can allow hot water to pass through the coil. This unwanted heat enters the airstream and warms the space. The thermostat responds exactly as designed. It increases the flow of cool supply air through the VAV box to offset the unwanted heat from the leaking heating valve. As a result, the system simultaneously heats and cools the same space. Because the thermostat continues to maintain room temperature near set point, occupants often remain comfortable, unaware that a significant amount of energy is being wasted. The energy loss can continue indefinitely without generating comfort complaints that would trigger an investigation. The first slide in this video illustrates the VAV box and reheat coil operating as intended. The second slide demonstrates how a defective reheat valve can create substantial hidden energy waste while room temperature remains normal. Many of these systems are configured with a 50% minimum airflow setting, a practice that can create additional energy waste. This issue can be corrected and is examined in a separate video. In many buildings, the absence of comfort complaints is mistakenly interpreted as proof of efficient operation. In reality, control systems can automatically compensate for equipment failures, hiding substantial energy waste for years. Understanding control logic is essential if hidden energy losses are to be identified and eliminated. This drawing illustrates a properly operating VAV box with an associated reheat coil. The thermostat sends signals to both the control valve and the VAV box. As the room temperature rises, the room thermostat gradually closes the control valve, reducing and eventually stopping the flow of hot water into the reheat coil. As the room continues to warm, the thermostat then modulates the VAV box from its minimum ventilation setting up to its maximum airflow setting, as determined by the design engineer during system commissioning. The minimum airflow setting is established to satisfy building code requirements and indoor air quality standards. This drawing shows the same VAV box and reheat coil, but in this case the control valve has a defective seat. As a result, even when the valve is commanded fully closed, hot water continues to leak past the damaged seat and flow through the coil, causing the room to overheat. As the space temperature rises, the thermostat responds by signaling the VAV box to gradually increase cooling airflow in an attempt to offset the unwanted heat coming from the faulty valve. In the condition illustrated here, the VAV box has reached maximum cooling capacity, operating at 100% airflow, yet it still cannot counteract the excess heat being introduced into the space. This type of issue is surprisingly common in commercial buildings and often goes completely unnoticed because the temperature change may only be a degree or two, which occupants typically do not detect. However, the space is effectively being heated and cooled at the same time, resulting in significant and unnecessary energy waste. On our website, apscontrols.org, there's an article titled Fighting Climate Worry. Within that article are links to two reports that are highly significant when considering the future of today's children. The first is a BBC report indicating that more than 50% of children are regularly worried about climate change. The second is a Stanford University report projecting that the world could exhaust its economically recoverable fossil fuel resources within the lifetime of the children living today. These findings underscore the importance of taking climate change challenges seriously and pursuing practical, effective solutions. Just as importantly, we need to demonstrate that meaningful action is being taken, helping to reduce the anxiety many young people feel about the future. With respect to controls logic and energy conservation, it is important to understand that no solution can be applied everywhere. What we are really teaching is comparable to teaching someone how to play chess. We can show you the moves and strategies that have been proven successful in addressing conservation challenges in the past, but we cannot predict every situation you will encounter in the future. For that reason, I encourage you not to simply memorize the concepts presented in the APS training manual. Instead, strive to understand them deeply. A thorough understanding transforms information into a practical tool that can be applied to new and unforeseen challenges. As Albert Einstein famously observed, information is not knowledge. Information alone has limited value. Knowledge is gained when information is understood and can be applied effectively in the real world. Thank you very much for your efforts with respect to climate change, and I believe that collectively, with everybody trying, we can make a major impact on the threat to the children's future.